Hello and good evening everyone. Welcome to this NPTEL PMRF session on real-time digital signal processing. I am Shohardo Ghosh, a first-year PhD student in the Department of Electrical Engineering at IIT Gandhinagar. I have completed my BTech as well as MTech from IIT Kharagpur in the Department of Electronics and Electrical Communication Engineering with specialization in microelectronics and relay design. Today we are in week 6 and we shall be covering the following topics: circular convolution, we shall do a brief revision, then we shall talk about FFT using the overlap add method, and then the FFT using overlap save method, and finally we shall end the talk with the correlation between two signals and the signal with itself, and some brief practice of questions. Today's section will be quite short because of the lesser amount of material covered in this week's lecture. Please let me know if my voice is audible as well as my screen is visible if anyone is present in the session. Okay. So let's get started. So now we look into the topic of circular convolution. So basically, how does this come into a picture when we have this linear convolution? So the last time what we talked about was, let's say we have a signal xn which is of length L point, it's an L point sequence, and then we have a sequence h of n which is our filter coefficient, which is m point, which is an m point sequence. So when we do xn convolution with hn, we get yn, which is an L plus m minus 1 point sequence. Okay, so now what happens is that when we do direct convolution, sometimes we want the signals to be not implemented directly using convolution because of the number of multiplications and adds involved. So what we often want to do is that convert them into frequency domain. Okay, like xn is converted into frequency domain, hs is converted into frequency domain. Okay, and then we obtain some, let's say x of k, h of k, and we multiply the two in frequency domain. The resultant is suppose y tilde of k, and we perform inverse frequency transformation to get back our signal in the time domain. We get y tilde of n. Now in our real-time computers, the frequency domain transformation that we use is DFT. So what does a DFT do? DFT transforms an endpoint sequence into another endpoint sequence from the frequency domain to the transform domain. Sorry, from the time domain to the frequency domain. But now here is a catch. This xn is an L point sequence and hn is an m point sequence. So similarly, their transforms x of k will also be an L point sequence and h of k will be an m point sequence. Now what happens is that since these are different point sequences, so they cannot be multiplied. Okay, they cannot be multiplied. So often what is done is that, suppose now let us go into circular convolution. So what happens is that whenever we have some signal y1 of n which is an endpoint sequence and we convolve that, sorry, I should not say convolve now, and there is a sequence y2 of n, that is also an n-point sequence. So their normal convolution, or what we call as the linear convolution, gives us a 2n minus 1 point sequence. But however, when I do y1 of k, means after doing the DFT of y1 of n, when I obtain y1 of k and similarly y2 of k, I multiply these two and then obtain something as z of k. Okay, so if I do an IDFT of this, I obtain some z of n, but then we also realize that the z of n is a n-point sequence. Okay, this is a n-point sequence. However, when we realize that this is an n-point sequence, so it's obvious that Zn is not equal to y1 of n convolved with y2 of n. Okay, so then what is it? It turns out that it is something of the form yz of n is y1 of n. Okay, this is what we call circular convolution, and the symbol that I have shown over here, there I've given written n because it is in both of them are n-point sequences, and then I've enclosed it in a circle denoting it is an n-point circular convolution. So how does it behave, or what does it behave like? So let me take an example and then I will show how I'll help you understand how it behaves. So let's say y1 of n is all ones. I'm taking n equal to 4, and then y2 of n is minus 1, 0, 2, 1. Okay, so how does it behave? Let me tell you. So these are n equal to 4. Now let's try to do something. Let's first go through the normal linear convolution approach and see what we get. 1, 1, 1, 1. I am listing all the y1s in elements over here and y2 elements over here. Minus 1, 0, 2 and 1. So here I multiply them element by element. Okay, so it will be all repeating stuff. I had covered them in the previous week's lecture. Now I enclose them using these diagonals, and now I add each of these diagonal elements. How? Minus 1 is as it is, so minus 1 added with 0 is still minus 1. Minus 1 added with 2 is a 1. Now when I add all these, I get 2 plus 1 is 3, 3 minus 1, 2. And then I add them 0, 2, 1, I get a 3. And again 2 and 1, I get 3. And again here there's a 1 alone. This is my linear convolution as expected. Okay, and as mentioned earlier, this is a 7-point sequence. But what happens in circular convolution? Let us write the elements separately. So in circular convolution we are supposed to have n equal to 4-point sequence. So what happens in reality is that here let's suppose we write each of them one by one. So it's a minus 1, I wrote that. Now another minus 1 I write over here, another 1, then a 2. Okay, so we have completed 4 elements over here. Now this is the 4th element. So this 4th element actually we write over here. This is the 4th, this is the 5th, and this is the 6th. Okay, so what we do is that we break them into blocks of 4. So after this we can assume it's a 0 and then add them. When we add them up, what do we get? minus 1 and 3 is 2, minus 1 and 3 is 2, 1 and 1 is 2, 2 and 2 is 2. Okay, so what we end up getting is 2, 2, all 2's. So this is the result of the circular convolution. Okay, and so we observe that because of the circular convolution, in order to keep the lengths of both the sequences same, we end up getting something which is not the same as circular convolution. So oh hi, hello Anup, good evening. So is my screen visible? It's blank, right? Okay then. Also share the movement and stop sharing or in terms of wait a second. It's visible now? Okay, just hold on a second, let me check whether the recordings. Oops, so let me first. Recording is taking place, good enough. Okay, now you can see the screen, whatever contents I am showing. Okay, good. So let me review. Actually I was all alone, so I was recording it alone, so let me repeat it for you once again. I have no issues. Okay, so yeah, so in week 6 what we are doing over here is that basically this week's content is actually quite less, so I will be I'll complete it much faster. So first I will be doing a revision of circular convolution, and then there are two FFT methods or implementation. First is the overlap add, then we have the overlap save method, and then finally I'll talk about correlation. Okay, so when we talk about circular convolution, yeah, anything to say? Hello? What? I didn't get you. Hello? Okay, fine. Okay, so what I was telling just a few minutes back was that we'll start with circular convolution. So here we have xn as an L point sequence, and then we have hn as an M point sequence. Now when I convolve xn with hn, I get a sequence yn, which is an L plus M minus 1 point sequence, as we had discussed earlier. Now let's suppose that I don't want to do this filtering or convolution directly. I want to do this in frequency domain rather than directly implementing it time domain. So what we do is that we transform xn into frequency domain x of k, hn into frequency domain h of k. We multiply this x of k and h of k to obtain y tilde of k, and then we transform it back into our time domain. We get something y tilde of k n. Now we mentioned that the transformation that we do in frequency domain is the DFT, discrete Fourier transform. So x of n is a n-point sequence, and that when you transform to x in frequency domain x of k, that's also an n-point sequence. Now the problem that was arising was that the x of n is an L-point sequence, which I had mentioned over here, and h of n was an M-point sequence. Now so automatically the transforms are L and M-point sequences, but since their transform lengths are different, they cannot be multiplied. So we have to look for alternatives. So now we again visit back to the case of same length sequence. So let's suppose y1 is an n-point sequence and y2 is also an n-point sequence. So if we are supposed to have something like linear convolution, we get a 2n minus 1 point sequence, because n plus n minus 1. Okay, so we have the corresponding transform y1 of k and y2 of k, which are also n-point transforms. We multiply them and obtain some n-point sequence again, Okay, that's z of k. If I take the IDFT, inverse discrete Fourier transform of this z of k, I obtain something called z of n. This time domain, this is also an endpoint sequence. But then I realized that this is endpoint and their convolution is 2n minus 1 point. So obviously they are not the same. Zn is not equal to y1 and convolution y2 of n. So what is it? It is actually what we were terming as circular convolution. The notation for circular convolution, what we do is that the number of points n, and we enclose that by a circle. So rather than star, we denote it by this in this thing. Okay, so then I started with an example that y of n, let's say all of them are ones. We take an n equal to 4 point sequence, and then we have y2 of n, which is minus 1, 0, 2, 1. Okay, now let us first do the linear convolution. So Arup, do you know this method? I had shared in last class how we do the linear convolution. This technique, this method, how to do. Anup, are you there? Hello. So are you okay with this convolution? How this convolution is done? Do you know this method? The ones that I've shown over here. Okay. Okay. So do you follow something? So do you follow something like let's say minus 1, 0, 2, 1. So you write minus 1, 0, 2, 1. Okay, these, right? This is minus 1, 0, 2, 1, then minus 1, 0, 2, 1, then minus 1, 0, 2, 1. Then you add them up like this, right? Yeah. So this is lots of methods now. Okay. So whatever method you do, let's say let me try your method as well, and then I do. So we had y1 of n as 1, 1, 1, 1. y2 of n as minus 1, 0, 2, and 1. Now when I do the convolution, what do I get? Let's say these are fixed impulses. So minus 1, 0, 2, 1, minus 1, 0, 2, 1, minus 1, 0, 2, 1, and minus 1, 2, 0, 1. Okay, so I get a minus 1, I get a minus 1. Here 2, 0, 1, they add up to get a 1. 1, 2, minus 1, that's a 2. Okay, so they are all matching up. So irrespective of however you do, the answers must be the same. 2 plus 1, 3, 2 plus 1, 3, and here you get 1. Okay, so this was a sequence which we get in the normal linear convolution. But when we want to do circular convolution, what we do is that we were trying to use a n equal to 4 point sequence. So what will we do? We will try to break this into a sequence blocks of 4. Now here there is 3 elements, so I just append a 0 to it, and what I do, I then add these 2 blocks, minus 1, 1, 2, 3, 3, 1, 0. Okay, now I add them, what do I get? 2, 2, 2. Okay, so this is the circular convolution of y1 and y2. Is this clear how I have done this circular convolution? Actually what happens is that it is not that I take, it is the mechanism of circular convolution. So what circular convolution is doing is that circular convolution convolves an endpoint sequence with another endpoint, and the resultant has to be endpoint. Okay, so in reality what is happening is that when you have a long sequence, okay, something like this, you have long sequence, so what convolution does is that it actually aliases this. Just like in frequency domain you had aliasing, right? Similarly in time domain you see the data stamp. Let me give the data stamp 0 1 2 3, and here 4 5 6 and 7. But if you see 4 5 6 7, if I do the mod of 4 modulo, you know, n mod m, which means the remainder when you divide n by m. Okay, my screen is not visible now. Oh, okay, small, it is small. Okay, yeah, I'm going back. Yeah, so okay, let me write them here. So it was how much? -1 -1 1 2 3 3 1 0. If I look at their indices, okay, n, this one is z of n, and I look at the n, this is 0 1 2 3 4 5 6 7. And what circular convolution does is that, let us do n mod n. Okay, you know what is mod operator? Okay, so what mod operator does is that, let me write it, modulo operator. Let's say I want to do a mod of b. So what it is the a, if you have done programming, then you might be knowing this, a percentage b, or in other words, remainder obtained while dividing a by b. Let me give you an example that will clear it all. Let's say I want to do 7 mod 4. So what does that mean? When I divide 7 by 4, 4 ones are 4, the remainder is 3. So 7 mod 4 is 3. 27 mod 2, since this is 27 is an odd number, so the remainder will be 1. 6 mod 42, 6 is less than 42, so 42 times 0 times 6, remainder will be 6, so this is 6. Is this modulo concept clear? Okay, so when I keep writing numbers like this, 0 1 2 3 4 5 6 7 8 9 10 11. Okay, now let's say I want to do, this is n. Now when I say n mod 4, what will happen? 0 0 0 1 2 3, because these are less than 4, so it will be as it is. Now here 4 will again become 0, 5 will give 1, 6 will give 2, 7 will give 3. This point is clear. 4 divided by 4 gives remainder 0, 5 divided by 4. Okay, similarly n 8 9 10 11, I'll get 0 1 2 3. So what happens is that whenever the indices x of 0, x of 4, x of 8, all of them will get added together. Okay, and they will give me y of 0, x of 1, x of 5, x of 9, all of them will be added and they will give me y of 1. Okay, so that's why, because this is the actually a property of circular convolution, because of which we are adding all of them, like -1 and 3, all of them are at modulo will be 0. -1 and 3, they are located modulo 1 position, 1 and 1 are located modulo. So you see I am adding them all together. Okay, that's why I have done like this. Okay, so this was all about circular convolution. Let me clear the space. Okay, leave. So So that was our circular convolution. Let me give the tick mark over here. Now we will talk about FFT overlap add method. Did you watch my previous lecture on FFT or normal FFT? This overlap add and overlap save method does not actually require FFT. So do you want me to cover FFT, revise FFT, or should I continue directly with overlap add and overlap save? I could not get you. There was a lot of noise behind you. Nope, I could not get you. Can you please? Yeah. Okay, so you were saying I do not need to cover teach the basic FFT, right? Okay. Okay, then you may refer to the week 5 lecture for my FFT details. So I've covered a lot of things in that. So what is this FFT overlap method used for, or if overlap add or overlap save? So it is used for linear filtering of long duration signal. Okay, so what happens is that our signals in real life, let's say before sampling, okay, so these are very long sequences. Even let's say I record a speech or a lecture of 30 minutes, okay. Now we know that, let us suppose that our speech, maximum speech content is restricted to 4 kilohertz. Oh wait, listen, somebody is joined. Okay, so let us suppose that our Fmax, does somebody want to say something? Okay, muted. So our speech is limited to, let's say, 4 kilohertz, and let's say I am sampling it at just the Nyquist rate, although I should do it at more, so 8 kilohertz, or 8 kilohertz meaning 8 into 10 to the power 3 samples per second. Okay, so if you want to see numbers, in 1 second I will have 8000 samples. Okay, now when I have a 30-minute speech, so how many seconds is that? 30 times 60, which is 1800 seconds, and that 1800 seconds would imply how many samples? 1800 times 8000 bare minimum. I mean, for high quality you need to oversample this. So we will have something like 144 times 0.50 to the power 5, 1.44 times 10 to the power 7 samples. So imagine, when we talk about FFT, we talk about endpoint FFTs. Okay, now if I want to take this XT signal XN, so XN is how much? 1.44 times 10 to the power 7 sample sequence. Now imagine if I do 1.44 times 10 to the power 7 point FFT. We had learnt in the previous lecture that it has a multiplications, complex multiplications of the order n by 2 log 2 base n. Complex, and if you try to see actual number of multiplications, it will be more than that. Multiply that by 4 and something, there will be some factors. So if I try to calculate it for this, just even if it is logarithmic, I am calculating it on the calculator. It requires almost 171212871. So it's like one multiplications, complex multiplications are required, these many. Now imagine trying to have so many multipliers on your chip. So what is the order? 1 2 3 4 5 6 7 8. So almost like you're just less than a billion multipliers. We talk about billion transistors on a chip, but your chip has billion multipliers. So you can imagine how much area, how much power, how much delay would be involved in this. So it is really foolish. Or even if we talk about entire signal, I have talked about a recorded signal. In real life, you may want to some live streaming of some concert is going on, and you want to process that signal. So the signal will keep on coming. You will have no end to the number of samples. So what we actually do is that you understood the complexity, right? Why I am saying that this one it's really complex to work on a single frame of signal. Anu, Pratibha, is it clear why I was talking about this? Okay, so what we actually do over here is that when we have these blocks of signal, this long signal, we break them into several blocks, several individual blocks of some very small length, some 10 milliseconds, something like that. Okay, and then we process these signals individually. So that's why I said it's a technique of linear filtering of long duration or online signals. So let's start with some of the math. So let us denote the filter coefficients h of n. Let's assume this is a length m, and our input signal x of n we break into segments of length L. So what we have over here, x of n this is one block x1 tilde of n of length L, another block x2 tilde of n, another block x3 tilde of n, length n. Okay, so all of these are of length L, but we know that an m point signal when convolved with an L point signal gives L plus m minus 1 point sequence. Okay, so what should we do? We actually form this x1 of n by taking x1 tilde of n and okay, so we take x1 tilde of n and append zeros to it. How many zeros? We append m minus 1 zeros to it. Similarly, we have x2 of n. How do we obtain x tilde of n, this block, and we append m minus 1 zeros, and similarly we do with this with all the L point blocks. So when I write them, okay, oops. So when I write them, how does it look like? X of 0, x of 1 till x of L minus 1, and append them with m minus 1 zeros to make of length L. x2 of n will again start, since it's ended at x of L minus 1, I start at x of L plus 1 all the way till x of 2L minus 1. This is becoming a length n. x3 of n gives x2 of L plus 1 all the way till x of 3L minus 1. Again I add these extra zeros to make them of length n. And what do I do with h of n? I create something h tilde of n, which is h of n along with some appended zeros. How many zeros do I append? L minus 1. So this is m point and this is L minus 1, so I have length n. So all that I have obtained over x1 of n, x2 of n, x3 of n, h tilde of n, all of them are now endpoint sequences, which is the same as the convolution length L plus m minus 1. Okay, n. L plus m minus 1 is equal to n. So now what we do? We first evaluate y1 of k equal to x1 of k times h tilde of k. So these are the DFTs. x1 of k and h tilde of k are the DSTs of x1 of n and h tilde of n, which have been obtained by FFT. So actually in machine or in the chip you will use FFT algorithm or the FFT architecture, but for our hand-drawn purposes we will not worry about what is the FFT going on. And the corresponding output y1 of n will be the IDFT of y1 of k. Okay, is it clear up to this point? What have I done over here? Shabarish? Oh, it's clear, right? Okay. So now what we'll do, we will again repeat step 3 for y2 of n, y3 of n. What we will do, we will take x2 of n and then its corresponding FFT, multiply that with h tilde k, and then again take IDFT. Do the same for x3 of n, you will get y3 of n. Now what we will do, we will add all m minus 1 samples of each output. How will we do that? Let me show you. So when you have this y1 of n is an endpoint sequence. What we'll do, we'll take m minus 1 point from this, and then we have y2 of n, m minus 1 from here. What will we do? We will add them. Okay. Similarly, here we have m minus 1 points. We have y3 of n over here. Here also we have m minus 1 first point. We will add these two. Here also we have m minus 1 from the last and m minus 1 from the first, and this will keep on going. So what we do, keep this as it is. Keep it as it is. This is the added portion of the m-1 points. Keep it as it is. This is the added portion. So you see, there is an overlap and there is an addition going on. There is an overlap and there is an add. Okay, so this is why it is called an overlap add method. And FFT, where is this being used? It is being used in the x1k h tilde k calculation. Okay, let me solve an example over here. Let us take h of n 3, 2, 1, 1. So here m equal to 4. And what is our xn sequence? 1, 2, 3, 3, 2, 1, minus 1, minus 2, minus 3, 5, 6, minus 1, 2, 0, 2, 1. In this we will assume that we are taking block lengths of L equal to 4. So what is n? N is m plus L minus 1, which is 7. Okay. Now let us divide our blocks. 1, 2, 3, 3, 2, 1, 1 minus 2, blocks of 4, another block of 4, another block of 4. So what do I have over here? x1 of n is 1, 2, 3, 3, and I want to make it a 7-point sequence. I have 4 points, so I should add 3 more zeros. Similarly, x2 of n and 3 is m minus 1. x2 of n 2, 1, minus 1, minus 2, 3 zeros. x3 of n is minus 3, 5, 6, minus 1, 3 zeros. x4 of n is 2, 0, 2, 1, and then 3 zeros. And what will be our h tilde of n? It was our 3, 2, 1, 1. I want to make it a 7-point sequence. So 0, 0, 0. Now what do you need to do? First you find y1 of n is x1 of n, 4-point convolution with h tilde of n. So what is it? 1, 2, 3, 3, 0, 0, 0. 3, 2, 1, 1, 0, 0, 0. Let's do the linear convolution sum. 3, 2, 1, 1, 0, 0, 0. 3, 2, 1, 1, 0, 0, 0. 4, sorry. 6, 4, 2, 2, 0, 0, 0. 9, 6, 3, 3, 0, 0, 0. 9, 6, 3, 3, 0, 0, 0. All of them are zeros. It's just that the sum is quite long, otherwise everything's good on the machine. Now I divide these segments.
बिल्कुल सही बात कर रहे हो. हम लोग ना ये ट्राई कर रहे हैं जो हम लोगों ने बच्चों के लिए स्पेशली करता था बनवाया था, तो हम उसमें ट्राई कर रहे हैं कि बच्चों को सुबह का जो 6-6:30 बजे वो भी
So I have divided these segments,
बच्चे शाम को बाहर बैठे ताकि
and when I add them up I get the linear convolution as 3
ट्राई करें, मतलब लास्ट
8
टीचर दिन से बहुत जल्दी ना हमने बच्चों के
14 18
बच्चों के प्रैम पे
11 6 3 and then 1 2 3
हम उस पे भी बच्चों को
4
बार वॉक
5
कराएंगे।
6 1 2 3 4 5 6. So this was our linear convolution, but then we are actually doing a circular convolution, and circular convolution is of length 7. Okay, so 1 2 3 4 5 6 7 this, and then it will be added with this block. I had explained just a few minutes ago, but these are all zeros. So our first block y1n is 3 8 14 18 11 6 3. Is this clear how I got this y1 of n?
हर एक चीज में नेगेटिविटी दिखती है, प्यार नहीं दिखता, और कुछ चीजें ऐसी भी होती है जो इंसान हर चीज ना कैमरे के आगे नहीं शो कर सकता। ये चीजें नहीं बताई जाती कि मेरे अपने लिए, मेरे अपनों के लिए क्या किया।
Now we obtain y1 to obtain y2 of n. y2 of n is x2 of n or x tilde of n. So I straight away write the answers so that time saved. So it is actually 6 7 1 minus 5 minus 4 minus 3 minus 2. I will take y3 of n, do the convolution. One side of the convolution I get minus 9 9 25 11 9 5 and minus 1. y4 of n is x4 of n, 4-point convolution with x tilde of n. What do I get? I'll get 6 4 8 9. So these are very simple things, only a lot of calculations and writing is involved, so I'm not discussing them further in detail because I've already discussed them here. So again, repeating the same does not make any sense. So you see over here we have obtained our y1 of n, y2 of n, y3 of n and y4 of n. Now we shall add all of them. How? 3 8 14 18 11 6 3, and we need to add the last m minus 1 samples to the first m minus 1 samples of the next block. 4 minus 3 minus 2. This one is y1, this one is y2. So this is minus 9 9 25 11 9 5 minus 1 6 4 8 4 3 1. So what will I do? I'll perform this. So we have overlapped all of them. We shall now perform the additions over here. Okay, these encirclements are the additions. 3 8 14 18. I guess these are not visible properly, so I'll use some other pen. 3 8 14 18 17 13 4 minus 5 minus 13 6 23 11 15 9 7 4 3 1. So this is the final output y of n, which we have done using overlap add method. Okay, so you can verify this by the long method also. So what we have done in external overlap add, so we have break the data into chunks of L. Our filter is of length m, and then in order to do the proper convolution or the multiplication in frequency domain, we append them by zeros. All these blocks of length L are appended by m minus 1 zeros, as you can see over here, to form them of length m. Similarly, h tilde of n is of length m, so we append them by L minus 1 zeros. Now you take their FFTs and then multiply them to obtain the discrete Fourier transform of the first block out by 1 of n, which is the IDFT. Once you take the IDFTs of the first block, we will add the last m minus 1 samples with the first m minus 1 samples of the left block. Then the y2 of n, last m minus 1 samples of the y2 of n with the first m minus 1 samples of y3 of n. Okay. And this keeps on happening. So you see that if you have the code or the circuit to do this last sample with the first sample, last m minus 1 to first m minus 1 addition, this is iterative. So this is continuous. You can do it for all incoming streams of data. So you don't have to use a lot of hardware in this. So I hope you understood how this overlap add is helpful. Okay. So you have solved overlap add method. Now we shall go into the overlap save method. This is also called the overlap and discard method. Why discard? I will let you know very soon. So once again, same we do use the same notation. Filter coefficient Hn of length m, input signal xn, block length L. So the filter output n equal to L plus n minus 1 point. So what we do to this x of n as always is broken into blocks of L, x1 tilde, x2 tilde, x3 tilde, and so on. Now what do we do with them? Now we take this block of length L, and for the first block I add m minus 1 zeros and here x1 tilde of n. Now look at this very carefully. What do we do with this second block? We take this block of length L and m minus 1 samples from this are added over here. This is our x2 of n. Now again look what I do over here. I take this block length L and I take m minus 1 samples from the end and append it over here. So how will it look like in the notation when I write it? So x1 of n is m minus 1 zeros, x of 0, x of 1 whole derivative, x of L minus 1, x2 of n, x of L minus m plus 1. We are taking the last m minus 1 samples. Whole derivative x of L minus 1, m minus 1, end samples of x1 of n, x of L plus 1 till x of 2L minus 1. So what will x3 n be now? x of 2l minus m plus 1 till x of 2l minus 1. These are the m minus 1 end samples of x2 of n. We have x2 of l plus 1 till how much? x3l minus 1. Is this clear whatever I have done till now? Pratibha, Shabresh. Any doubt, any confusion? Whatever I have done as of now. Okay. So what we do now? Just like the previous steps, I shall once again repeat them. I shall not repeat them over here. I copy it over here. So we have the same thing over here.
जैसे कि जिसका इवनिंग में रहता है और किसी का होता है लेट नाइट स्टडीज को करता है तो आमतौर पर 3-4 को वो सोता है तो उसका जगते जगते
So the same thing over here. See, h tilde of n is h of n appended with l minus 1 zeros. All of them are length n sequences. This is length n, this is length n, this is also length n. And then we evaluate y1 of k is this x. x1 is different, but still we take its FFT and obtain x1 of k, h tilde k. Similarly, we obtain y2k, y3k, and so on. Then take its IDFT to obtain, or actually bracket में IFFT, y2 of n, y3 of n, and so on. Okay. Now what do we do with them? First, m minus 1 samples of y1 of n, y2 of n, so on are discarded, and remaining samples, L samples, are fitted one after the other to get the final sequence. So what do you obtain? y1 of n is actually an endpoint sequence. So this m minus 1 over here I discard. Similarly, I have y2 of n over here, m minus 1 samples and L. What do I do to the m minus 1 samples? Discard, and then I have the y3 of n, m minus 1 samples and then L of them. What do I do with them? Discard. So, and I do keep doing that for all the possible, all the blocks that keep on coming to me, and then I merge all of these. y1 hat of n, y2 hat of n, y3 hat of n, all of them are L length sequences. Okay, so because I see these are overlapping, over there they also overlapped, and here they are being discarded, and this is the, or you can say I'm saving these, rather to say I was saving these. I was saving the previous m-1 samples, so that's why it's called an overlap save or overlap discard method. Is the entire procedure clear, everyone? Okay, okay, good. So we shall solve another example here. Here what do we have? We have h of n as 1 1 1. So what is our m? M is 3. And what do we have xn? Our input signal 3 minus 1 0 1 3 2 0 1 2 1. Okay, so what will we take? We will take blocks of length, how much? L equal to 6. So m is 3 and L is 6. So what is n? M plus L minus 1, that's an 8-point sequence. So what will be your h tilde of n? It's 1 1 1, but we need 8 points, so we add 5 more zeros. H tilde of n is done. Now what are our blocks of data? We need to take blocks of length 6. 1 2 3 4 5 6. And then we also need to ensure that m minus 1, which is 2 samples from the previous one, are taken. So what do we take over here? We take this subset 6 and 2 of them overlap and save them. x1 of n is what? We add m minus 1 zeros in the beginning and then our usual block 3 minus 1 0 1 3 2. x2, what will it contain? These m minus 1 previous samples, then our normal block. Okay, done. So now what do you want to obtain over here? Yeah, y1 of n. So y1 of n is x1 of n. What is n over here? N is 8. So you can form an A50 circuit out of that, n equal to 8 as well. H of n. So let me add on x1 on the vertical side, 0 0 3 minus 1 1 3 2 1 1 1 0 0 0 0 and another 0. So let me put them all down in places. 3 3 3 all zeros, minus 1 minus 1 minus 1 0 0 0 3 3 3 2 8 2. Now we divide them into blocks. So actually what will happen is that we will get this linear convolution result as 0 0 3 2 2 0 4 6 5 2 1 2 3 4 5. But then our n was equal to 8, so we will take blocks of 8 1 2 3 4 5 6 7 8. Okay, this is a block, this is another block. Now we 1 2 3 4 5 6 7 8 0. Okay, so now you add them. So 5 and 2 are behind, so they come in front. So you get 5 2 3 2 2 0 4 6. This is the y1 of n. Similarly, we obtain y2 of n and no more writing using x2 of n, an 8-point convolution with h tilde of n, and that's 3 5 5 3 3 4 3 1. Now let me show you the addition. What is to be let me show you the addition that is to be done. So we have y1 of n. What's that? 5 2 3 2 2 0 4 6. m minus 1 m minus 1. Over these m minus 1 you start the next sequence of y2 of n. 3 5 5 3 3 4 3 1. Now what does the overlap and discard method say? Remove the first m minus 1 samples from each block. Remove the first m minus 1 sample from each block and fit the rest of them. So let's see how they fit into 3 2 2 0 4 6 5 3 3 4 3 1. So this is your final output. This is your yn. So we have done the overlap, save or discard method. So another purpose behind showing these techniques was to ensure that you are able to solve the assignment questions which are there in this week's sheet. So now that I have shown, you should be able to solve them on your own and correctly. So overlap save method has been done. So is overlap add, overlap save method clear to all of you? Overlap add and overlap save. Okay, very good. Okay, now let's go back to the final topic. And that is correlation. So correlation. So this is actually an important quantity in statistics. How does it help? Let's say you have two quantities. X is the number of hours spent in solving numericals. This is a random variable. Another random variable Y, that is the, let's say, all India rank in GATE examination. Okay, so what we do is we plot a lot of we get a lot of statistics from all around our country. We do surveys from various colleges, acquire their ranks as well as their number of hours spent in studying. So hoping that everything, all the data plotted is true. So corresponding to each student, we obtain a lot of data points. Okay, so for every student I will obtain this point, and then I keep on dotting all of them. So you can see it's getting a bit messier over here, but I hope you are able to see the trend that is being shown over here. Okay, so what are you able to see over here? You see, as you increase the number of hours spent in solving numericals, you observe that more and more number of students are getting better rank. I mean, here actually Y should not be the all India rank, it should be the score actually, because if your all India rank is 1, then you are down here, so it should rather be your GATE score. Okay, so now it makes sense that as you increase number of hours spent in solving numericals, your GATE exam score improves in general. You can see, because even at the same number of hours spent in solving numericals, let's say over here you have some students getting a lower score, some students getting very high score. Okay, and this randomness is due to certain other things which we are not taking into account, and this is an error, this is a random error, and this is the randomness which comes in the picture. But then we see there is an overall, if we try to fit a kind of line in between this, we get a line with a positive slope. Okay, so this is something that we call positive correlation. Okay, similarly I can give another example. Let's say X is the price of tomatoes. We know what happened recently in our grocery stores, sorry, not grocery stores, the vegetable markets. RV, random variable Y, is our market sales. So can anybody please tell me what will happen over here? What do you expect to see? Pratibha, Shavrish, what will happen over here? If my price of tomatoes increase, what will happen to my market sales? Okay, so correct. So that's what we had observed in our just a few weeks back. I said the previous month only. So as your price of the tomatoes decrease, sorry, it has decreased now, but as it increases, the sales amount severely decreases. People stop buying tomatoes, or decreased the amount of tomatoes they are buying, So what do you see over here? The data points are having some kind of opposite relationship. As your x increases, as you move downwards, you see lower number of cells coming into picture. So if you fit in a negative line, you see a line with a negative slope. This, unlike the above one, is something that we call negative correlation. This is something that we talk about from a statistics point of view, but this is something that we talk from a statistics point of view, that you have two random variables and how closely they are correlated. You have another case that is zero correlation, which may not make where two random variables may not make any sense. Let me think of an example. So x is the size of your shoe and y is the CGPA in 8th semester. So what do you obtain? We'll obtain some kind of a cloud. So it will be something like this, where there is no correlation, so you call that zero or no correlation. The size of shoe has nothing got to do with a CGPA in the 5th semester. Okay. Similarly, signals, we have done this for random variables. So signals also have their correlation. Let's say we have a signal xn deterministic. Okay, let's say these are two deterministic signals of length n. So we can actually quantify their correlation and rather cross correlation as cxy of k is limit n tends to infinity 1 upon n summation over 0th index to the last index x of n y of n minus k. Okay, so how does it help us in real life? Lots of applications. I'll give you a simple one. So let's say you have a radar antenna at your base station or a ground. You are trying to look for an enemy missile or an enemy plane. Okay, so what will happen? You will send some pulse signal x of t. X of t will be something like this, and this is this kind of a system is actually duplex, so you're receiving and sending simultaneously. So when there is, so what happens if you know the principle of radar? So this will actually go hit this and come back. So before you actually get the reflection, when there is no reflection, your output yt is actually some noisy signal because of the noise around the environment, noise in the electronics. But when you have a reflection, the signal that you get is something, you get back the pulse, so you get something like this. Okay, and this distance tau, the time after, sorry, this time tau is 2d upon v, where d is the distance between the radar station and the plane, okay, and v is the velocity of the propagating wave, okay. So now what is actually done is that the very simplest way, the very easiest way to actually determine the distance is you take correlation of xt and yt. So when you actually find cxy of t, will obtain, you'll see that what happens. Let me plot each of them. You have x of t over here and y of t. So when you do x of t into y of t, that's completely 0. But then when you do, let's say I shift yt over here, x of t times y of t plus tau, so xt, and actually this should also have been a noisy waveform, xt and y of t plus tau, very high value, say 10 to the power 5. It may not retain something like that, but we get a very high value. So this when you evaluate the cx of t, then let's say at minus tau you get a very high value, and overall it's 0, okay. So the peak actually helps us understand that when the reflection came back to us, so how good the signals are correlated is actually shown by this correlation. Is this clear? This radar, how it worked in the radar situation? Okay, good. So this was a small application, and let me do a small numerical. So let's say x of n is 2, 0, 0, 1 and hn is 4, 3, 2 and 1. We have to find the cross correlation between x of n and h of n. So what we actually do is that the cross correlation can actually, if you look at the summation, it is like 1 upon n summation x of n times h of n minus k, okay. So if you look at it more deeply, it's like 1 of n, 1 into n, x of n convolved with h of minus n. So in order to obtain the values, what do? We first shift h of n. H of minus n is 1, 2, 3 and 4. Now we perform xn convolved with hn. 2, 0, 0, 1. Sorry. 1, 2, 3, 4. 2, 4, 6, 8. 0, 0, 0, 0. All zeros. 1, 2, 3, 4. Add them up. 2, 4, 6, 9, 2, 3, 4. And now we have to divide them by 4 in order to normalize this. You obtain 0.5, 1, 1.5, 2.25, 0.5, 0.75 and 1. So how do we find the 0? So where is the 0 point? This is a sequence, but we don't know is 0 point. So how do we obtain 0? So k equal to 0, which means xn and hn are directly multiplied and divided by 4. So when does this happen? 2 into 4. So I am directly multiplying them. 2 into 4 plus 1 into 1 by 4, that's 9 by 4. So the point where you get 2.25, that's your k equal to 0. Okay, so this is your you cap n. Yeah, cap n is 4 over here, length n. N is what? Actually means why we are dividing, right? So actually you do not need to divide, but based on the lecture that was given in the course, I am showing this division sign. So the main thing that they say is that you have to normalize it. That's why you give this capital N. But you may not use it. Since many like in other books also you may or may not find this N. So it's like a normalizing factor. You do not need to worry too much about it. For this course you divide it by N, but for the rest of your other applications, depending on the requirement, you may or may not divide by capital N. So actually in real life what happens is that you are not worried about the actual values. You are rather worried about where you get the maximum value. 0.51, 1.5, 2.25, 0.5, 0.75, 0.1. So whether it is something like this or whether it is scaled down by some value, let's say if it's even bigger, it doesn't make any difference, right? I need to know where it is maximum. Okay, I need to know where it is maximum. That's why and that's what is my importance. And this is the place where these two you see over here, n equal to 0 is highest, so xn and hn are directly have the maximum correlation when they have no shift. Okay, no shift difference. And we have, in order to obtain better estimates, if you want to avoid this 1 upon n thing, what we often do, we have another thing which is called the correlation coefficient, sorry for the wrong number, which is rho x y of k is cxx, sorry I'm writing the auto, cx y of k upon cx y of 0. So in this case you see, even if you don't take 1 upon n, you still get the same value, and it's better to work with correlation coefficient because it is always normalized between 1. So a value of -1 stands for 100% negative correlation, 1 stands for 100% positive correlation, 0 stands for no correlation. Okay, I did something wrong. It will be actually this. So the quantity cxx of k is actually called the autocorrelation coefficient. It's a simpler version of the correlation that we just learned. What is it? It is 1 upon n summation n equal to 0 to n minus 1 x of n minus k, convolving with itself. And okay, so like you often have questions in GATE related to correlation. You may have like Rxx of k is x of n convolved with x of minus n. So when you take its Fourier transform, the Fourier transform of autocorrelation is something called the power spectral density mod of x omega whole square. And when you have some quantity, signal going through a filter f of n, with y of n if this has a correlation, sorry, this is a PSD, power spectral density. I hope that you already know these things because it was a part of the prerequisite. And this has a Fourier domain representation h of omega. And if we want to find the power spectral density of our output, so how do you obtain? Sy by omega is mod of h omega whole square times sxx of omega. Okay. So is the correlation coefficient and the basics behind it, is this clear to everyone? Hello, am I audible? Hello? Anyone there? So, okay, relation. Very good question. Very good question. Is so. Before explaining this, let me tell you. So we have completed all the 4 topics that were supposed to be covered in today's video. Sorry, in today's lecture. So whatever I have taught in this section in today's class is good enough for solving the assignments in provided. And if there is something that I have not covered in this, that means that has already been covered in the previous week's lectures. So you need to refer to the previous week's lectures. I have also uploaded the handwritten notes on the Drive link. Okay, so let me answer the question about the power spectral density and the cross correlation. Okay, so what happens is that, okay, let me take the example of AWGN, additive white Gaussian noise. Okay, so what does this kind of a noise property have? What kind of a property does this noise have? So the property that this noise, let's say this noise is in discrete domain, is that expectation of noise n of k times n of k minus m, which equals the rxx of m, is sigma square noise power or the noise variance times delta of k minus m. Now it might look abstract, let me explain it in a better way. Do all of you understand what additive white Gaussian noise is? I hope it was covered in communication systems. Does anybody require any understanding in this brief explanation? Okay, so you know about it, right? Your voice is inaudible. What are you saying? I can just... Okay, good. So when you look at the autocorrelation function of this AWGN, it's actually the Dirac delta function. So 0, 1, 2, minus 1, minus 2, minus 3. So what does it say? So you can see over here that if this signal is only related with, let's say you have a noise sample over here at time 0, okay, and it's obvious that a signal is related with itself, okay, like you are your own self 100%, okay. So let's say a person A and a person B. If you compare a person A with himself, the comparison is 100%, right? He is 100% similar. But if you compare A with another different person B, he'll be less than equal to 100%. Equality does not make sense in comparing persons, but in signals it may be 100%. Okay. Similarly, a sample you can consider sample as a person. So a sample when compared with itself is always the same, so it's 100%. But when I say expectation of nk times n of k minus m, it means that how close or how closely related is the next sample to the first sample. Or in other words, can I have some kind of predictability? Can I have some kind of a guess, a good guess or a wild guess about 1 given 0? So since our autocorrelation is 0, correlated, it is uncorrelated. See, what did I say over here about uncorrelated? In the example, the size of your shoe has nothing to do with the CGPA in the 5th semester. So whatever be the size of your shoe, your CGPA is independent of that. Similarly, whatever be the next index, the value of the next index will not have any correlation, any dependence on the previous. So it will be, can be anything. There is no correlation. It will be anything. It's wild. Okay. Now, when you talk about it, look its power spectral density. Its power spectral density is flat. So what does it mean? Since this is a wild sequence, okay, very wild sequence. So what does wild sequence means? Wild sequence means lots of variations, okay, lots of variations. And when you have lots of variation, it means you have all or several kinds of frequencies. So when you see the AWGN, which is the wildest of all possible signals, it means that you are, and if you see the PSD, it has uniformly distributed uniform power spectral density, which means it has equal amounts of low frequency components, equal amounts of medium frequency, equal amounts of high frequency components. Okay, so it has contributions from all kinds of variations. But now if you have some kind of a signal which is like periodic, okay, periodic. So what does this periodicity show? It means that I have some kind of a predictability. If I know this, I know it will move up, I know it will move down, I know it will move down, I know it will move up. There is some kind of a predictability, some kind of a correlation, some kind of a relation. When you have relation, you have more knowledge, you have less variation. Okay, you have less variation, and when you have less variation, you seem to have a fixed frequency, and when you have a fixed frequency, your power spectral density will be more concentrated around some sort of a lower value. Okay, only few frequencies will be obtained, rest of them will be low. Okay, this is how you can see them in sort of in the perspective of random signals. Okay, for random signals this view is very good, and you can easily extend it to this normal deterministic signals. So correlation over here is showing the kind of power content. Over here the signal is deterministic, we have the power content. I hope this is intuitively clear to all. Was this clear? Okay, so that's it for today, everyone. I hope you enjoyed the session. Okay then, good night. I am closing the session here.
और हमारे यहाँ की खवातीन के दो बड़े प्रॉब्लम है। जब वो बहू बनती है तो उन्हें अच्छी सास नहीं मिलती, जब वो सास बनती है तो उन्हें अच्छी बहू नहीं मिलती।